Good evening, everyone. Good evening. Good evening. I welcome you all again to the JEE Enthuse. Hope all of you are doing great, having the good time at home. Well, people, if I'm audible and visible to everyone, hit the chat box with the thumbs up. Let me know if I'm audible and visible to everyone. Hi, Nishant. Hi, Sahana. Hi, Kirito. Hi, Jumana. Hello, Fida. How are you guys doing? Good evening. Good evening, everyone. Good evening. Good evening. Welcome to the session. Welcome to the session. Good evening, Uncharted. Good evening. What's up? How are you guys doing? How are you guys doing? Let me know in the chat box. Let me know in the chat box. Let me know in the chat box if you guys are doing wonderful. Yes, that's great. Hi, Shrivani. Hello, how are you? Wonderful, guys. Great. So, people, as you all must be knowing, today is our 5th session from the chapter Chemical Equilibrium. Yes. Till now, we have talked about the degree of dissociation. We did the KP-KC calculations, and in the today's session, we are going to talk about the degree of dissociation in terms of vapor density measurement. Yeah, we are going to talk about the degree of dissociation in terms of vapor density measurement. Yeah. Hi, Nishant. Hi, cool girl. Good evening. Good evening. Welcome. Welcome to the session. Alright, guys, so before starting the session, let me introduce myself. As you all must be knowing now, my name is Wassim Sir and I'm your chemistry master teacher right here. Okay, so people, this is the schedule of the week. This is the schedule of the week which I have been following. Yes, so people, today is our 5th session of the chemical equilibrium, and in this week we are going to finish this chemical equilibrium off. Yeah. Okay, and people, on Sunday you have got the Menti quiz from the chapter Chemical Equilibrium with me on this channel at 9 p.m. Yeah. Okay. So on Sunday, you have got the Menti quiz from the chapter Chemical Equilibrium at 9 p.m. on this channel with me. Right. And people, you are done with the Tuesday's Menti quiz with the Shimon Sir. And on the, I think you are done with the physics Menti quiz as well with Shreya Sir. Yeah. So stay prepared about the Menti quiz, which I'm going to take on Sunday at 9 p.m. from the chapter Chemical Equilibrium, which will be finishing on Saturday. Okay. So people, before starting, do like the video, share and subscribe the channel at the same time so that everyone will get benefited out of these sessions, right? Okay, before starting the session, I need to give you the brief introduction about the Vedantu JEE Pro Subscription. What all benefits you guys are going to get into this, okay? Let me tell you guys, if you are enrolling yourself in the Pro Subscription, if you are getting this Pro Subscription, first thing, you guys are going to get the 5,000 plus hours of live online teaching, regular tests and assignments will be provided to you, which contains more than 10,000 questions. We have got 20 plus teachers with 5 plus years of experience will be training you personally for the upcoming JEE 2021 as well as 2022. Yeah, and you have got the option to learn either in English or in Hindi. It's completely your wish to select the language, get trained by the master teachers of Vedantu in your physics, chemistry as well as mathematics. Yeah, and people, let me tell you, at the end we are going to cover everything which includes your micro as well as crash courses right here. Okay. For the ones who are going to appear in JEE in 2021, we have come up with 3 different plans, and on every plan right here, we have got 50% off for you, okay? 1 month, 3 month and 6 month plans, okay? After the discounts, it's going to be 3.75k, 10.5k and 27k respectively, okay? And all these 3 plans are valid for the ones who are going to appear in JEE in 2021. And in all these plans, you have got 50% off right here, okay? Yes, Anurag, after this, I'll be doing the ionic equilibrium. Yes. Moment thermodynamics, okay, thermochemistry also will be doing, just wait for that. Alright, for the ones who are going to appear in JEE in 2022, we have come up with 4 different plans. On every plan, you have got again the 50% off right here. 1 month, 3 month plan, 6 month plan, 12 month plan, okay? And after the 50% off, you guys are just getting it for 2.5k, 6.75k, 12k and 21k respectively, right? And people, this 50% off, this is valid in all these 4 plans, okay? And all these 4 plans are valid for the ones who are going to appear in JEE in 2022, okay? Now, how to get enrolled in this, how to get these plans, let me tell you, there is a link in the description box of the video. You just have to click on that link. You have to use the coupon code as WBPRO. On using this coupon code of WBPRO, you guys are going to get 50% off in whatever plan you're selecting for yourself, yeah? Alright guys, so let me know if you guys are super duper excited for this today's session or not. Let me know in the chat box if you guys are super duper excited for this session. Yes. Yes, Anurag, I'll be doing that. I will be doing that. I already take the classes, yeah? Kirito is saying, Kirito is super duper excited. Sahara is super duper excited. That's wonderful. Hi, Darshini. Welcome, welcome, welcome. Hi, Amir. Hi, Janani. Good evening, good evening. Good evening. Nishant is saying Josh is very, very high. That's actually great. That's actually great. Hi, Jatin. How are you doing? Welcome to the session, bro. Welcome to the session. Okay, so without wasting a lot of your time, let's get started with the vapor density measurement. So first of all, I'll make you understand what this vapor density of the gas is all about, okay? What do we mean by the term vapor density? Let's talk about that vapor density first, okay? First thing, guys, how do we define this term vapor density of the gas? Let me tell you, vapor density of the gas is the ratio of density of the gas to the density of hydrogen gas when the pressure and temperature of the gas is kept fixed, is kept constant, okay? How do we define the vapor density of a gas? Vapor density of a gas is nothing, it is just the ratio of density of the gas to the density of hydrogen gas, okay, when the temperature and the pressure of the gas is kept constant, okay? Very, very simple term, okay? Just the ratio of the density of the gas to the density of hydrogen gas when the temperature and the pressure of the gas is kept constant, right? Now we will see. Let's say I have got an ideal gas in the container. Let's say I've got an ideal gas in the container, right? If I have got the ideal gas in the container, can I say it's going to follow the equation PV equal to nRT? Yes. If I'll be having the ideal gas in the container, it's going to follow the equation PV equal to nRT, correct? Now people, the ideal gas which is in the container, let's say this ideal gas is kept at constant pressure and temperature. Pressure and temperature of this ideal gas is kept constant, okay? I do not have to let the gas to change its pressure or temperature, correct? Now people understand guys. P is the pressure of the ideal gas, V is the volume occupied by the ideal gas, N is the number of moles of the ideal gas, R is the gas constant, T is the temperature of this ideal gas, yeah? I can say that, okay? Now we will see. I can write it like this, PV is equal to N is the number of moles of the gas. Number of moles of the gas is going to be simply given mass of the gas divided by molar mass of the gas multiplied by R multiplied by T, yes? People, if I can shuffle this equation a bit, I can write it as Pm is equal to W divided by V multiplied by R multiplied by T. Yes. What do we call this term, guys? W by V, mass by volume. Do we call it as density? Yeah. Should I be calling it as density of the gas? Absolutely. So people, I got one simple relation. Pm is equal to dRT. Yes. Pm is equal to dRT. This equation we have discussed in detail in your states of matter chapter, and this equation is what we call as density form of the ideal gas equation, yeah? Where P is the pressure of the gas, M is the molar mass of the gas, D is the density of the gas, R is the gas constant, T is the temperature of the gas, okay? Now guys, understand. See, I have kept the gas at constant pressure and temperature. The gas is kept at constant pressure and temperature. And R value, it's already constant. So can I say at constant pressure and temperature, more density of the gas is directly proportional to molar mass of the gas? Yes. I can say at constant pressure and temperature, density of the gas is directly proportional to molar mass of the gas. So people, in this equation, wherever you are seeing the term density, replace the term density by the corresponding molar mass of the gas, okay? Wherever in this equation you are seeing the term density, replace that density term by its molar mass, yeah? At constant pressure and temperature, correct? So I can write it like this. I can write the vapor density of the gas equal. It was density of the gas. So instead of density of the gas, what should I write? I should write molar mass of the gas. Yeah. I should write molar mass of the gas divided by. This was density of H2. Instead of this density at constant pressure and temperature, I should be writing molar mass of H2. Yes, I'll be writing molar mass of H2 gas. Absolutely. Correct? Now, as you all must be knowing, molar mass of H2 gas is simply 2 grams per mole. Yes, molar mass of H2 gas is 2. So people, can I get a simple relation right here? Molar mass of a gas is always equal to 2 times its vapor density. 2 times the vapor density of the gas. This is something which I want you guys to remember right here. Molar mass of the gas is equal to 2 times the vapor density of the gas. Anurag, regarding the books, Shimon sir has taken the session about the books. You can go to the playlist, you can check it out. Okay, he has given you the correct idea about which all books to follow in physics, chemistry as well as mathematics. Yeah, still I'll be taking one more session on that as well regarding the books and everything. Okay, so people, I want you guys to remember this relation right here. Molar mass of a particular gas is always equal to 2 times the vapor density of the gas. And how do we define the vapor density of the gas? First of all, vapor density can be only defined for a gas when the gas is kept at constant pressure and temperature. When the pressure and temperature of the gas will be kept fixed. Okay, and vapor density of the gas is always equal to the density of the gas divided by density of hydrogen gas, provided the temperature and the pressure of the gas is kept fixed, is kept constant, right? So simple relation I got from here. Molar mass of the gas is always equal to 2 times the vapor density of it, right? Now we will understand what do we have to do right here with this vapor density term, correct? People, I'm going to give you a formula right here. I'm going to give you one important formula right here, which you are going to use in order to calculate the degree of dissociation of a particular reaction right here, okay? If this is alpha, which represents your degree of dissociation, yes, and degree of dissociation, I'm giving you one formula, which is capital D minus small d divided by small d multiplied by n minus 1 right here, okay? So I'm not going to derive this formula, neither you want it, okay? Simply I'll show you the application of this formula. How do we apply this formula? And then we calculate the alpha value of the reaction. We calculate the degree of dissociation for a particular reaction, okay? First thing, guys, what is this capital D right here? Remember the terminologies, guys. Capital D is the theoretical vapor density. It is called as the theoretical vapor density, or in simpler words, so that you can remember it, let me write it like this. It is what I'll be calling as, capital D is what we call as vapor density of reactant, at time t is equal to 0. Vapor density of reactant at time t is equal to 0. That means vapor density of this reactant when the reaction has not started, okay? Okay? And this D is the vapor density of the reactant at time t is equal to 0, which is going to be molar mass of the reactant at time t is equal to 0 divided by 2. Yes, remember this thing first of all. This capital D is what we call as theoretical vapor density, or we call it as vapor density of the reactant at time t is equal to 0. We represent it by capital D, which is going to be molar mass of the reactant divided by 2. Yeah. Now people, this small d is what we call as vapor density of the equilibrium mixture. Vapor density of the equilibrium mixture. What do we mean by that? Okay, let me first of all make you understand few things right here, then I'll make you understand what is this vapor density of the equilibrium mixture all about, right? Let's say, guys, at time t is equal to 0, I have got A moles of this reactant. This is going to be 0. Yes. And I'm assuming this is one balanced chemical equation, and over here your stoichiometric coefficient is 1. Over here your stoichiometric coefficient is n. Let's assume the degree of dissociation of this reaction is alpha. Correct? People, when equilibrium will be attained in the reaction, can I say I'll be left with A minus A alpha moles of this reactant? Okay. Now people, 1 mole gives n moles, so A alpha moles are going to give me n A alpha moles, correct? Can I say these are the moles of reactants and products at equilibrium? Yes, when equilibrium will be attained in the reaction, these are going to be the moles of this reactant, these are going to be the moles of this product at equilibrium. And people, this reaction will be taking place in a closed container. Yes, this reaction will be taking place in a closed container. So can I say at equilibrium I'll be having few moles of gas A as well as few moles of gas B? Okay, so can I say at equilibrium I'll be having a gaseous mixture right here? I have got the gaseous mixture right here. Whatever will be the vapor density of the gaseous mixture at equilibrium, that I'll be representing by small d. Small d is the vapor density of the equilibrium mixture right here. Small d is the vapor density of the mixture at equilibrium right here. Okay, understand, guys. And remember, this small d value, it will be always given to you in the question. Yeah, the small d in maximum questions, it will be given to you. Okay. And if people, in some questions you'll get confused which one is your capital D, which one your small d, remember capital D is always going to be greater than your small d. Capital D is always going to be greater than the small d. Okay, In a question, if you get confused sometimes, like which one to take as capital D, which one to take as the small d, remember a trick, remember a shortcut. Capital D will be always greater than small d, okay? The value of D which is going to be more, that is going to be the capital D value. The value of D which is going to be lesser, that is going to be the value of small d, first of all, yeah? Now people understand one more thing. What is this n, right? See, we talked about this capital D, we got to know what is the small d, okay? What is this n right here? What is this n right here? N is simple thing, guys. Let me write a reaction right here. Let's say I've got a reaction PCl5 gas in equilibrium with PCl3 gas plus Cl2 gas. Yes, is the reaction balanced? Absolutely, the reaction is balanced, yeah? Now people, over here the stoichiometric coefficient is 1, over here the stoichiometric coefficient is 1, and over here the stoichiometric coefficient is 1. Can I say 1 mole of PCl5 gives 1 plus 1 mole, that is 2 moles of products? 1 mole of PCl5 is giving me 2 moles of products. Yes, so I would say n value for this reaction is 2. The number of moles of products which you get from 1 mole of reactant is the value of n, yeah? Over here, you can have a look. From 1 mole, I'm getting n moles. That is this is the value of, this is your n right here. Similarly, in this reaction, 1 mole is giving me 2 moles. So the value of n is 2. So the value of n is 2. The value of n is 2. Yeah, very simple. Let's say I'm taking one general reaction so that you can understand it properly. Let's say I've got a reaction as A gas in equilibrium with 4 times B gas plus C gas. Yes, this is the reaction which is at equilibrium. Now people, from 1 mole of A, how many moles of products I'm getting? 4 plus 1, that is 5 moles of products I'm getting. From 1 mole I'm getting 5 moles, so I would say the value of n over here is 5. Yeah, value of n over here is 5. Okay, now people understand, I need to use this formula to calculate the degree of dissociation of certain reactants right here. Okay, and how do we do that? That is the point. Okay, for that I'll be directly moving to the questions, but before going on to the questions, I want you guys to remember again, your capital D is the vapor density, is the theoretical vapor density. It is the vapor density of the reactant at time t is equal to 0, which is going to be molar mass of the reactant divided by 2, and D is what we call as vapor density of the equilibrium mixture which we'll be having at equilibrium. Yeah, and N is nothing, number of moles of products which we get from 1 mole of reactant. Okay, right? And if in a question you get confused which one to take as a capital D, which one to take as small d, remember capital D will be always greater than your small d. Okay, now people, I'll give you some certain questions. By doing certain questions, you'll get to know properly how do we use this formula. Yeah, okay. See guys, this is something called as theoretical vapor density of reactant, or we call it as vapor density of reactant at time t is equal to 0. Yeah, D is the experimental vapor density of the gaseous mixture at equilibrium. Okay, and N is the number of moles of product formed by the dissociation of 1 mole of the substance. Yeah, this is something which I told you few minutes back, correct? Now people, this is the first question which is on your screen, right? Let's try to do it and let's get to know how to use the formula which I gave you right here in order to calculate the alpha. Okay, understand properly what I'm going to say. Yeah, why don't you have to talk, you have to see for 1 mole. You don't have to check the 2 moles. You have to see how many moles of products will get formed from 1 mole. Okay, I'll give you examples as well, just wait for it. See guys, the vapor density of N2O4 and NO2 mixture at a certain temperature at equilibrium is 30. Yes, let me write the terminologies once again. Small d is the vapor density of the equilibrium mixture, What is capital D? Capital D is the vapor density of the reactant at time t is equal to 0. At time t is equal to 0. N is the number of moles of product. Which gets formed from 1 mole of your reactant. Yes. Now people, first thing I'm given with the reaction right here. Let me write the reaction over here. Very simple. It is N2O4 gas is in equilibrium with what? It's in equilibrium with 2 times NO2 gas. This is the reaction which is given to me. Yeah, this is the reaction which is given to me. Okay, now people, the vapor density of N2O4 and NO2 mixture at equilibrium is 30. Vapor density at equilibrium, that is denoted by small d. So I'm given with the value of small d right here. Yes, small d value is given to me as how much? It's given to me as 30. Yes. Calculate the percentage dissociation of N2O4 at the same temperature. Okay. We need to calculate the percentage dissociation. We need to calculate the percentage dissociation. How do I do that? How do I do that? First of all, from 1 mole of N2O4, how many moles of NO2 are getting formed? 2 moles of NO2 are getting formed. So can I say N value for the reaction is simply 2? N value for the reaction is simply 2. Now people, if I need to calculate the value of capital D over here, what is capital D? Capital D is the vapor density of the reactant at time t is equal to 0, which is going to be molar mass of the reactant at time t is equal to 0 divided by 2. What is the molar mass of this reactant, guys? These are 2 nitrogens, so 14, 14, 28, 28 plus 64, 28 plus 64, that is 92 divided by 2. Value you'll be getting as 46. Yes, so this is the value of capital D. You can check it out. Small d is less than capital D. Yes, small d is less than capital D. So people, I will be simply using the formula which I gave you right here. Alpha is equal to capital D minus small d divided by small d multiplied by n minus 1. Yeah. What is the value of capital D I got? I got the value of capital D as 46 minus what is the value of small d which we got? That is 30 divided by small d value, that is 30, n value 2 minus 1. Yes. So people, if you will solve this, you will get the alpha value as 0.53 right here. You'll get the alpha value, degree of dissociation as 0.53 right here. But am I supposed to calculate degree of dissociation or percentage dissociation? I'm supposed to calculate percentage dissociation, and in the last session, if you remember, I gave you one more formula. Percentage dissociation is always equal to alpha multiplied by 100. Since I got the alpha value, I just have to multiply it by 100. So it's going to be 53% right here. So the percentage dissociation of this N2O4 right here is the 53. Yeah. Very, very simple question. Let me know in the chat box if it's clear to you. If it's clear to you fast, yeah? Let me know in the chat box if it's clear to you so that I can move on to one more question, right? Let me know in the chat box fast. Hi Gopal, what's up? Wonderful, guys. Great. Let's move on and let's talk about few more questions. Okay. This is the question which is on your screen, guys. This is the question which is on your screen. This is the question all about. Is this? Yeah. In the reaction, understand the terminologies first, then you can do the question properly. Yeah. In the reaction, the vapor density of the mixture, that means he's talking about the vapor density of equilibrium mixture, which is denoted by D. Yes, which is denoted by small d. Vapor density of mixture is reduced to half. Vapor density of the mixture is reduced to half. The initial vapor density of the reactant is capital D. At equilibrium it is small d. So the vapor density of the equilibrium mixture has reduced to half. So it's going to be capital D divided by 2. Yeah, small d is equal to capital D divided by 2. Very simple. Now people, if the degree of dissociation, it's not degree of dissociation, if the percentage dissociation is 25, percentage dissociation is given as 25. Yes, calculate how many moles of B will be formed at equilibrium on starting with 2 moles of A. All right, let's try to do it. See guys, I'm given with a reaction A gas in equilibrium with what? In equilibrium with NB gas. I do not know the value of N right here. So what I'll be doing right here first, see, small d is equal to capital D divided by 2. Percent dissociation is given. Can I get the alpha value? Alpha is always percentage dissociation divided by 100. If you remember, it's going to be 1 by 4. This is the alpha value, yeah? I got the first thing, I got the alpha value. Now, how to approach this sort of equation? See guys, we know the formula which I gave you a few minutes back. Alpha is equal to capital D minus small d divided by small d multiplied by n minus 1. Yes. What is alpha all about? We got the value of alpha as 1 by 4, which is going to be equal. Capital D I'm writing as such minus small d I'm writing capital D divided by 2. This is small d again in the denominator, which is capital D divided by 2 multiplied by n minus 1. Yeah, I can say that. Okay. Now we will see. This is going to be 1 divided by 4 is equal. Can I take this d common right here? If I'll take the d common right here, it's going to be 1 minus 1 by 2. That's going to be 1 by 2. Yeah, divided by. This is going to be d by 2. This is going to be d by 2 multiplied by what? Multiplied by n minus 1. This d and this d got cancelled. This d and this d got cancelled. Yeah. Is it clear to everyone? Over here I have 1 by 2, over here 1 by 2, so it will get also cancelled. So I'll get n minus 1 is equal to 4. N value I got as 5. Since I got the value of n, People, if I got the value of n, my actual reaction is going to be like this then. If I got the value of n, my actual reaction is going to be A gas in equilibrium with Nb instead of n, I'll write 5b. A gas in equilibrium with 5 times B gas. Yeah. What do we have to calculate basically? We have to check how many moles of B are formed from the 2 moles of A. How many moles of B are formed from the 2 moles of A? That's what we need to check, right? Let's assume the degree of dissociation is alpha. Alpha value we already know, which is 1 by 4. Yes. On starting with 2 moles of A. At time t is equal to 0, I'm given with 2 moles of A. So A value is 2 right here. It is going to be 0. Yes. So people, at equilibrium, can I say it's going to be 2 minus 2 alpha? How it used to be A minus A alpha. So it's 2 minus 2 alpha. So 1 mole gives 5 moles. So 2 alpha moles will give 5 into 2 alpha. That means 10 alpha moles. Yes. Very simple. So people, can I say 1 mole gives 5 moles? So 2 alpha moles are going to give me 10 alpha moles. So the moles of B which I'm getting at equilibrium are going to be 10 alpha. So the number of moles of B at equilibrium which I'm supposed to calculate is basically equal to 10 multiplied by alpha. And alpha value we already know, that is 1 divided by 4. Yes. So you're going to get the value as 10 by 4, which will be 2.5. Yes. So 2.5. So 2.5 moles of B will be getting formed right here in this reaction. Let me know in the chat box if it is clear to everyone. Let me know in the chat box if it is clear to everyone. Yes. Yes. This question was asked in your JEE once, yeah? Let me know in the chat box if it is clear to every single guy, yeah? Okay, let's move on then. Let's move on to one more question. Let me see if you can solve that or not. Okay, one more question we have. Vapor density of the equilibrium mixture of NO2 and N2O4 is this much. This is the vapor density of equilibrium mixture. That means this is the value of small d. Yeah. Calculate the degree of dissociation. That's it. That's what is given to me. Calculate the degree of dissociation. Is anything else given to me? Second part is Kp for the reaction if total pressure is this much. Okay, I'm given with the reaction as well. What is my reaction all about? My reaction is N2O4 gas in equilibrium with what? It's in equilibrium with 2 times NO2 gas. This is the reaction which is given to me. First thing which I'm supposed to calculate right here, that is the degree of dissociation alpha. And we already know alpha is nothing. Alpha is capital D minus small d divided by small d multiplied by n minus 1. Correct? Now we will see what all values do I know. See, very simple. First thing, I know the value of small d over here, which is 38.33. Yes, this is the vapor density of the equilibrium mixture which is given to me. Yeah. Now we will at the same time, can we calculate the value of D? What is D? D is the vapor density of the reactant at time t is equal to 0, which is going to be molar mass of reactant divided by 2. Yes, it's going to be simply 46. Okay, what is the value of N? 1 mole gives 2 moles, so N value is simply 2 over here. I just have to put all the values over here. Should I be getting the value of alpha? Let me know the value of alpha, which you'll be getting right here. Let me know the value of alpha fast. It's going to be capital D. Capital D is nothing. It is 46 minus small d. Small d value is 38.33 divided by small d is simply 38.33 multiplied by n minus 1. That is 2 minus 1. That is 1. Yes. Let me know this value, guys, how much it comes. Let me know the value of 46 minus 38.33 divided by 38.33. Let me know its exact value right here. Let me know its exact value in the chat box fast. Let me know its exact value. Let me know the exact value of alpha right here. Yes. Yes. Ashwarya is saying it's coming as 0.2. Okay. All right. Alpha value you are getting from here as 0.2. Alpha value you got to know as 0.2. So my first part of the question is done and dusted. Yeah. My first part of the question is done and dusted. Now talking about the second part, calculate the Kp for the reaction if total pressure at equilibrium is 2 atm. Now people, there is one more assignment which is given to me right here. I need to calculate the Kp for the reaction when the total pressure at equilibrium is 2 atm. Yeah. I got the alpha value. Now, how do we approach this sort of the question? Say, second question. You already know, guys. I'll be writing the reaction again. N2O4 gas is in equilibrium with what? Is in equilibrium with 2 times NO2 gas. Yeah. 2 times NO2 gas. This is the reaction which is given to me. Okay, alpha value we already got. How much is that? That is 0.2. Correct? That is 0.2. Okay, now people, let's assume at time t is equal to 0, I have got A moles of this, I have got 0 moles of this. Let's assume that. So can I say at equilibrium, it's going to be simply A minus A alpha. Since 1 mole gives 2 moles, so A alpha moles gives 2 A alpha moles. Yeah. Yes. So these are the moles of N2O4 at equilibrium. These are the moles of NO2 at equilibrium. Yes. Now people, if I'll ask you how many total moles are there in the container at equilibrium. First of all, this reaction is taking place in a closed container. How many total moles are present there at equilibrium in the closed container? I'll say A minus alpha plus 2A alpha. Yeah. The total moles present at equilibrium are going to be A minus A alpha plus what? Plus 2A alpha. Can I say the value over here is going to come as A plus A alpha? Or I'll take the A common. It's going to be A into 1 plus alpha. Yes, these are the total moles present at equilibrium in the container. If I'll divide this term by the total moles present at equilibrium, which are going to be A multiplied by 1 minus alpha, A multiplied by 1 plus alpha. Just divide this term also by the total moles, which is going to be A multiplied by 1 plus alpha. Correct? So can I say this term is giving me the mole fraction of N2O4 at equilibrium? This term is giving me the mole fraction of NO2 at equilibrium. Yes. Now people, what all terms will get cancelled first? Have a look guys. First of all, this is the mole fraction of N2O4 at equilibrium. This is the mole fraction of NO2 at equilibrium. If I'll multiply it by the total pressure at equilibrium, I'll get the partial pressure of N2O4 at equilibrium. If I'll multiply it by total pressure at equilibrium, I'm going to get the partial pressure of NO2 at equilibrium. Yes. Is the total pressure at equilibrium given to me? Yes, it's given as 2 atm. Everything is given guys. First of all, see how many terms will get cancelled out. If I'll take A common in the numerator, that A and this A will get cancelled. So I'll get simply 1 minus alpha divided by 1 plus alpha multiplied by P. This is my partial pressure of N2O4 at equilibrium. Correct? Now this A will get cancelled. So I'm going to get the 2 times alpha divided by 1 plus alpha multiplied by P. This is my partial pressure of NO2 at equilibrium. I have all the values. Yeah. Do I have all the values? Absolutely, I have all the values. People, I know the value of alpha. I know the value of P. Okay, alpha value, we got to know 0.2. 1 minus 0.2 is 0.8. So it's going to be 0.8 divided by 1 plus alpha. 1 plus 0.2, that is 1.2 multiplied by total pressure is how much? Total pressure is 2 atm. So I'm simply multiplying it by 2. So I got the partial pressure of this reactant at equilibrium. Similarly, I'll get the partial pressure of this reactant at equilibrium as well. Alpha value is nothing. Alpha value is 0.2. So 0.2 multiplied by 2 is 0.4 divided by this is going to be 1.2 multiplied by total pressure is 2. So I got the partial pressure of each reactant and product at equilibrium. Since I was supposed to calculate the Kp expression, yeah, so I can write the Kp expression as partial pressure of NO2 at equilibrium. Partial pressure of NO2 at equilibrium raised power 2 divided by partial pressure of N2O4 at equilibrium. Yes. Do I know both the values? Absolutely, I know both the values. Partial pressure of NO2 at equilibrium. That's going to be how much? 0.8 divided by 1.2. That's going to be 0.8 divided by 1.2 whole square. Correct? Divided by partial pressure of N2O4. It's going to be simply 1.6 divided by 1.2. 1.6 divided by 1.2. So people, you will get the answer something like this: 0.8 ka square divided by what? Divided by 1.2. 1.2 will get cancelled. So this is going to be 1.2 multiplied by 1.6 right here. Let me know the exact value which you are getting right here. A lot of people are saying it's 1 by 3, yeah? Yes. Yes, are we getting it as 1 by 3? Are we getting it as 1 by 3? Let me know fast. It's simple, guys. 0.8, write it like this: 0.8 into 0.8. Write it as 0.8 into 0.8. Yes, this is going to be 1. This is going to be 2 times. Yes, so it's 0.8 divided by 2.4. 0.8 divided by 2.4, or I can write it as 8 by 24. 8 by 24 is simply 1 by 3. So Kp value I got as 1 by 3. Can you let me know the units of the Kp as well? Yeah, I got the Kp value as 1 by 3. Can you let me know the units of Kp as well? Absolutely, you can do that. Units of Kp are going to be atm to the power delta Ng. What is delta Ng for this reaction? 2 minus 1, that is 1. So its Kp value is going to be 1 by 3 Kp value is going to be 1 by 3 atm to the power 1. Let me know in the chat box if it's clear to everyone fast. Let me know in the chat box if it's clear to everyone fast. Yeah? Yes? 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 Wonderful, guys. So let's move on to one more question then. Let me see if you can solve that or not. Let me see if you can solve that or not. I'm sure this is clear to everyone. Yeah? Let's move on to one more question, guys. Let's move on to one more question. Again, a very, very simple question, and all these questions have been asked in your JEE examination, guys. Okay? If the percentage dissociation is 40, what can we conclude from there? Alpha is 0.4, 40 by 100, that is 0.4. At 400 Kelvin and 1 atm pressure. Calculate the vapor density of the equilibrium mixture. Calculate the vapor density of the equilibrium mixture. We are supposed to calculate the value of small d. Small d represents the vapor density of the equilibrium mixture. Isn't it simple, guys? Yeah? Isn't it simple actually? So I just have to use the formula alpha is equal to capital D minus small d divided by small d multiplied by n minus 1. Yeah? Alpha value, we know that is 0.4, absolutely, is equal to capital D. What is capital D all about? Capital D is the vapor density of the reactant at time t is equal to 0, and vapor density of the reactant at time t is equal to 0 will be molar mass of the reactant divided by 2. What is the molar mass of this PCl5? What is the molar mass of this PCl5? Molar mass of PCl5. Phosphorus is 31. Okay, phosphorus is 31. Chlorine is 35.5 multiplied by how many chlorine do we have? 5 chlorines do we have? Divided by 2. Yes, this is going to be the capital D value. Yes, this is going to be the theoretical vapor density value. Absolutely. Isn't it going to be 31 plus? This is going to be 5, 5, 25, 5, 5, 25, 27, 5, 3, 15, 15. This is 17. Yeah, 177.5. Okay, divided by 2. So what is the value of D which you are getting right here? It is going to be 5.7187310 208.5 divided by 2, which is going to be 104.25. So I got the value of capital D, I have the value of small d. Okay, no, I have the value of capital D, I have the value of alpha, and let's calculate the value of N as well. From 1 mole of reactant, how many moles you are getting? 1 plus 1, 2 moles. So N value is simply 2. Okay, so people, capital D I got. How much is capital D? Capital D is nothing. It is 104.25 minus small d value I got. No, small d I didn't get. I have to calculate small d, divided by this is small d, multiplied by n minus 1, n is 2 minus 1. Yes, people, did I get one equation with one variable in it? Yeah? Yeah? Very simple. So you can calculate it. You can let me know the value of D in the chat box afterwards. In the comment box, I mean afterwards, right? You can solve it out on your own, okay? It's okay, Anish, it's okay. You can watch the lecture afterwards, bro. Yes? Yes? Okay. Moving on, guys. Moving on to one more question. Wait. I think I skipped some question over here. Let me check it out once. I think I skipped one question. Okay, this is something which we are done with, yeah? This is something which we are done. Okay. This is also done. Just a second, guys. Let me see, did we skip something or not? This is also done. This was also done. Okay, this is also done. All right, we have not skipped anything. Okay. Let's move on and let's talk about the curve between capital D by D and alpha, okay? Nothing, Kirito, that was just to confuse you, bro. That's it. That is just to confuse you. That's it. Yeah? Okay. See, guys, the curve between capital D by D and alpha. Over here, you will get one more concept, and that concept will be using in the questions, okay? Understood. Understand. See, guys, we know alpha is capital D minus small d divided by small d multiplied by n minus 1. Yeah? Can I write it like this? N minus 1 multiplied by alpha is equal to capital D minus small d divided by small d. I can write it like this, absolutely. Yeah? Can I write it like this? N minus 1 multiplied by alpha is equal to capital D divided by small d minus 1. Okay. Can I write it like this? Capital D divided by small d is equal to 1 plus n minus 1 multiplied by alpha. This is something which I got right here. This is something which I got right here. Now we will, this capital D divided by small d I'm plotting along y-axis. This alpha I'm plotting along x-axis. Yeah, I'm plotting along x-axis. Instead of this capital D by small d, capital D by small d, can I write y? Yeah. Instead of alpha, can I write simply x? Instead of this whole term, can I write m, which is the slope, plus this 1 is the intercept. Y is equal to mx plus c. What is going to be the nature of the curve? Isn't it going to be a straight line? But that straight line won't be passing through the origin. That is going to have the intercept as well. Okay. What is the value of the intercept, guys? What is the intercept of this curve? I'll say intercept is the value of c. C value over here is 1. Yes. This is the value of intercept right here. If I'll ask you what is the slope of this curve, slope means the value of m, and the value of m right here is n minus 1. So slope of this curve is simply n minus 1. Slope of this curve simply is n minus 1. Yeah? Yes? Yes? This is something which I want you guys to remember over here. People, there will be certain questions. There will be certain questions in which you'll be given with the graph. From that graph, you'll be calculating the n value, okay? Sorry. From that graph, you'll be calculating the n value, and how you'll be calculating the n value? You'll be given with the slope. From the slope, you'll be calculating the n value, and that n value you'll be using in the equations, okay? Which we have already, okay? For example, let me give you a question. By that question, you'll get to know how this concept is used. Understand, guys. For the reaction, the curve between capital D by D versus alpha is shown below. Okay, this is the curve which is given to me, and the slope of this curve is given as 2. This is a hypothetical, okay, hypothetical value. Calculate the percent dissociation when experimental vapor density becomes equal to the theoretical vapor density of the equilibrium mixture. There is something wrong in the question, guys. Just a second. Becomes equal to, okay, fine, all right. See, no, it's not, it's perfectly fine. See, for the reaction, the curve between capital D by D versus alpha is shown below. Calculate the percent dissociation. We are supposed to calculate percent dissociation, and as you all must be knowing, percent dissociation is nothing. It is just alpha multiplied by 100. Yes, this is the percent dissociation. When the experimental vapor density means the vapor density of the equilibrium mixture, right? When the experimental vapor density becomes equal to half of the theoretical vapor density is D, and it's going to be D by 2. Yeah? Yes? Yes? Very simple. Yeah? You got it? Can you let me know the answer fast? Now? It is simple. When the experimental vapor density becomes equal to half of the theoretical vapor density, okay? Just keep the question till here. Just remove this part. Okay? Just keep the question till here, okay? Now do it. Let me know fast. People, very simple. I just now told you slope of this curve is the basically n minus 1. Slope of this curve is n minus 1. So slope of the curve from here, which is n minus 1, before 5 minutes we got to know that is 2. So n value right here I'll be getting as 3. I got the n value. Yeah, I got the n value. Okay. Now people, can I use the simple formula? Alpha is equal to capital D minus small d divided by small d multiplied by n minus 1. Okay. Yes, I can do that. So alpha value will be equal to capital D I'm keeping as such, minus small d will be capital D divided by 2 divided by small d is the capital D divided by 2 multiplied by n minus 1 value we got to know as 2. N minus 1 is 2. So n minus 1 directly I'm writing as 2. Yes, if I'll take D, this is D minus D by 2, that is D by 2. D by 2 got cancelled. So alpha value we got as 1 by 2. Correct? Alpha value we got. Since we got the alpha value, just multiply this alpha value by 100. So it's going to be 1 by 2 multiplied by 100. So the percentage dissociation is going to be 50 over here, which is what we were supposed to calculate. I'm sure this is clear to everyone. Hit the chat box with the thumbs up if it's clear to every single guy right here. Yes? Wonderful, guys. Okay, so people, with this I'll be ending the today's discussion. Okay, no, wait, there is one more topic left. I forgot. There is one more topic left. That's what we call as a reaction quotient. Your vapor density measurement is done. Now is one more. Okay, that is reaction quotient. It's a very simple topic, guys. It's a very simple topic. Okay, let's understand this simple topic as well. Let's understand this simple topic as well. Reaction quotient. What do we mean by the term reaction quotient? What is this reaction quotient all about? Okay, let's get to know about this reaction quotient. See, guys, very simple. It is defined as this reaction quotient. It is basically the expression of the equilibrium constant. The expression of the equilibrium constant at any condition apart from your equilibrium conditions. See, guys, first thing, I've got a balanced chemical reaction right here. Let's say this is one homogeneous gaseous phase reaction. Let's assume, right? Now, people, if I want to write the equilibrium constant expression right here, in terms of concentration, it's going to be concentration of C raised power N3 divided by concentration of A raised power N1 multiplied by concentration of B raised power N2. But people, I'm writing the equilibrium constant expression, but I'm writing it at any stage apart from equilibrium. Okay, whenever we write this sort of expression, whenever we write the expression of equilibrium constant at any stage apart from equilibrium, that's what we call as the reaction quotient, denoted by QC. Yeah, yes. So what is the difference between actual equilibrium constant and QC? QC is what we call as reaction quotient. This is the equilibrium constant. In the expression of equilibrium constant, we should know the equilibrium concentrations of all the reactants and products. These are the equilibrium concentrations of all the reactants and products over here. Now, when I'll be writing the same type of expression, but at any stage apart from equilibrium, I'll be calling that as reaction quotient. Yeah? Yes. Now, we will remember, as you all must be knowing, every reaction wants to attain equilibrium as soon as possible. Every reaction wants to attain equilibrium quickly. Every reaction wants to attain what? Equilibrium quickly. Yeah? Why is that? Because I have told you in the first session, at equilibrium, the entropy of the system is maximum and free energy of the system is minimum. Yeah? And whenever we'll be having a system at which its entropy is maximum, free energy is minimum, the system is said to be stable. Every reaction wants to attain equilibrium. Why? Because at equilibrium, the reaction will have maximum entropy, minimum free energy, that is maximum stability. Okay? So, people, every reaction wants its QC value to get equal to equilibrium constant value. Yes, every reaction wants to match its QC value with the equilibrium constant value. Okay, yes. Now see what I'll be doing right here. Remember and understand at the same time. Okay, first thing, every reaction wants to attain equilibrium. Why is that? Because at equilibrium, entropy of the system is maximum, free energy of the system is minimum, and these are the two parameters which define the stability of the system. Yeah, so at equilibrium your system is highly stable. Okay, and at the same time I can say in other words as well, I can say every reaction wants to match its QC value with the equilibrium constant value. Yeah. Okay, see, guys, very simple. If I'll be having any reaction whose QC value is greater than equilibrium constant, I told you Q value wants to get equal to K equilibrium. Now I have got some reaction whose Q value is more than equilibrium constant. What is going to happen at that time? First thing, let me write the reaction right here. Let's say we have got the reaction over here as N1A gas plus N2B gas in equilibrium with N3C gas plus N4D gas. This is the reaction which I have at equilibrium, for example. Okay, this is the reaction which we have. Okay, First thing, guys, understand one thing. If QC for this reaction is greater than K equilibrium. First of all, what is the expression for QC? First of all, let me tell you, at equilibrium, your QC is equal to K equilibrium, which is going to be what? I'm talking about at equilibrium, guys. At equilibrium, QC is equal to K equilibrium, which will be concentration of C raised power what? Raised power N3 multiplied by concentration of D raised power N4 divided by concentration of A raised power N1 multiplied by concentration of B raised power N2. Yes. Now people, if I'll be having any reaction whose QC value is greater than KEQ, QC wants to get equal to KEQ, so what QC has to do? I should say QC must reduce its value. QC must reduce its value, then only its value will get equal to K equilibrium. Now the point is how QC will decrease its value. QC will decrease its value when when this numerator will decrease, and when this denominator will increase. Yeah. How will this numerator decrease? How will be this numerator decreasing? This numerator is the concentration of products. How will concentration of product decrease? When the backward reaction will proceed. So remember, whenever we'll be having the reaction whose QC value will be greater than K equilibrium, at that time backward reaction will be proceeding. Yeah? Yes? Sanjukta, I told you, every reaction wants its QC value to get equal to equilibrium constant. Yeah. Now, if QC value is greater than K equilibrium, QC will try to get equal to K equilibrium. So for that, what should happen? QC should decrease its value. How will it decrease its value? When this numerator will decrease. What is this numerator? This is the concentration of products. So concentration of products will decrease. How this concentration of products will decrease? When the reaction will proceed in the backward direction. Yeah. Yes. Pratik, we have discussed that, bro. For your reversible reactions, for the system, for the reaction to be at equilibrium, its delta G is 0, if you remember. Yes, and delta S total is also 0. We have discussed the criteria in thermodynamics. Okay. All right, guys, see. Now, people, the second thing. This was the first thing. Now, talking about the second thing. If I'll be having a reaction whose Q value will be less than K equilibrium, if I'll be having a reaction whose QC value is less than K equilibrium, first of all, this QC will try to get equal to K equilibrium. Now, I've got a reaction whose Q value is less than K equilibrium. So, Q will try to increase its value. So that it becomes equal to K equilibrium. Yeah. How will this Q increase its value? Q will increase its value if numerator will increase right here. What is this numerator? Numerator is the concentration of products. How will concentration of products increase? When the reaction will proceed in the forward direction. Yeah. I'll say forward reaction will proceed. Yeah. And at the same time, guys, if for any reaction QC value is equal to equilibrium constant, we say the reaction is at equilibrium. Yeah. Okay, so remember these three things right here. First one, if Q value is greater than K equilibrium, backward reaction will proceed. Second one, if Q value is less than K equilibrium, forward reaction will proceed. And third one, if Q value is equal to K equilibrium, reaction is at equilibrium. Yes. Very simple it was. Okay, so people, with this I'll take a leave. Okay, but before taking the leave, let me tell you, we are not done with the chemical equilibrium completely yet. We have to talk about the Le-Chatelier principle as well. Okay. Sorry guys, I think I'm getting cold. Yeah. Okay, so we have to do the Le-Chatelier principle. That will be doing the next session. Okay, and in the next session we'll be finishing this chemical equilibrium and we'll be starting the ionic equilibrium. And people, do not forget to attend the Sunday session at 9 p.m. in which I'll be taking a Menti quiz from the chapter Chemical Equilibrium. So people, for the ones who join us late, let me tell you, we are starting with the JEE 2021 crash course. In this JEE 2021 crash course on the actual Vedantu platform, we guys are going to cover your whole syllabus before your JEE 2021. We are going to train you personally in your physics, chemistry as well as mathematics. Yeah. So So do enroll in this program. You guys are highly going to get benefited from it, okay? And how to get enrolled in this batch? Let me tell you guys, there's a link in the description box for this crash course program as well. You just have to click on that link. You have to use the coupon code as WSCC. On using this coupon code of WSCC, you guys are going to get the discount, right? The actual price was 10,000, and after using this coupon code, you guys are just getting it for 8,000, which is very, very, very less. Yeah. Okay. There is one more link in the description box, which is for Telegram, guys. So do click on that link as well. Get added to the Telegram group, okay, and stay updated about the classes as well. And at the end, do not forget to like, share, and subscribe the channel so that everyone will get benefited out of these sessions. Yeah. So this was all from my side. Yes, this was all from my side. I'll see you guys tomorrow, okay, at 5:30, and we'll be finishing this chapter with the last topic, which is left in chemical equilibrium, which is again important, which is what we call as Lee-Chatlayer's principle, okay? So till then, you guys take care. Bye-bye. God bless you all and love you all. Take care, guys. Bye.